In the previous lecture, we saw the existence and uniqueness of Chern classes for complex vector bundles over topological spaces. Now, I wanted to recall the main steps. So the first point was to understand first Chern class. In that case, it was by definition and using the using the classifying space. And then we construct Chern classes using the projectivization of the given vector bundle, and then using splitting principle we prove uniqueness and also the properties by working on the projectivization bundle. So except for defining the first Chern class, rest of the things will progress somewhat similarly. So first Chern class we have to define by hand. So the question is, where will the first Chern class take values in? So for a given variety X, we have this homology ring, so which is direct sum of AK of X. But this is homology ring. Chern classes take values in the cohomology ring. So what is the value group for our Chern classes? So the point is, if X is non-singular, then later on in Fulton's book, so there is this notation where instead of indexing by dimension, let's say X is non-singular of dimension n, okay, non-singular variety of dimension n, then we define A upper K of X to be equal to A of n minus K of X. So the same thing, except the index as we are indexing by co-dimension rather than dimension. And in this case, the point is that this direct sum of AK of X is analogous to our singular cohomology ring of even, so let me say HI of 2 star X comma Z. So the even degree cohomology ring. Why even degree? Because this is going to be a commutative ring, and so this is this will be a ring. First of all, an intersection product will be constructed. So that is the name of the book, intersection theory. So AK, so there will be so given a class in AKX and ARX, we will construct a well-defined class. So Anand will construct a well-defined class in A of K R plus K plus RS, and this will become a ring. So this will be our value group for Chern classes when X is non-singular. But we will define Chern classes even for singular, not necessarily non-singular varieties, and the way we will do it as follows. So for example, we observe that given let's say a class in A, so like again X non-singular, this setup, and given a class in A upper K of X, just like in the topological case, singular cohomology acts on homology by cap product. In this case, using the intersection product which will be constructed later on, so alpha gives a map from let's say AI of X to AI minus K of X. What is this map? It is using the intersection product which will be constructed. So maybe I should state here. So there exists an intersection product AR of X cross AS of X to A R plus S of X, okay, which makes this into a ring, and it will satisfy all nice properties that one can expect. So pullback, preserving, basically well behaved with respect to flat pullback. So a cohomology class will give us an operator of degree minus K. So whatever that class is. So for any X, now not necessarily non-singular, and a line bundle, L, we will construct for the first Chern class as an operator from AKX to AK minus 1X. And when intersection product is defined, and so that is discussed in the lectures, it will be clear that this operator, when X is non-singular, is actually product with a degree 1 codimension 1 cycle. So this is what we want to. So for any X, we have to construct these operators. So this is for all K. Okay, satisfying properties that I will list. So this is the idea. So Chern classes in general for for the setup we are considering will be defined for vector bundle over any scheme, not necessarily non-singular, but they will be operators on this Chow groups indexed by dimension. Okay, so let us first understand three things. So one is Picard group, and let's say X is a variety of dimension n minus 1, okay, and an minus 1 X. So this is the Chow group of divisors. So take all divisors modulo rational equivalence, because this is dimension n, and an minus 1 is the Chow group of divisors. So we'll understand how this is related to this, and we are going to introduce one more player just because our schemes may not be non-singular. So this is the group of Cartier divisors. So I'll explain why we need to introduce this. So let me start by defining this. So how many of you have already seen Cartier divisors? Okay, quite a few of you have already seen it. So I'll go through the definition anyway. So a Cartier divisor on X, remember X is integral, so it has a function field, is a section of the sheaf Rx star. Rx was the function field, right? So Rx star modulo the sheaf of invertible functions, so O star, Ox star, okay. So let me spell out and say what exactly this is. So this is the constant. So this Rx is the function field of X, and for any open set the function field is the same. So this so if I take the non-zero elements of this function field, that gives me a constant sheaf on the variety, and the sheaf of units of my structure sheaf of rings, that is a subsheaf here, and I take quotient in the Zariski topology, and sections of this will be called Cartier divisors. Okay, so let us spell out what exactly this means. So a section of the quotient locally lifts to element is defined by elements of Rx star, but may not be globally, right? So therefore a Cartier divisor is defined or is given by an open cover. Let's say X is union of U alphas, and where F alpha is in Rx star, and instead of these F alphas matching on the intersection, they differ by a unit because they have to match in the quotient. So such that for all alpha comma beta, F alpha F beta inverse, this is in the sheaf of units. Okay, so that is the definition of a Cartier divisor. Of course, two Cartier divisors are equal if all these F alphas they differ by a unit, and then I have to also say how equality, what it means for equality when I change the open cover. So it's best to keep this as a definition and work with this when you want to actually work with it. So now the point is, given a Cartier divisor, so we can define a map from Cartier divisors to Zn minus 1x. Okay, so of course this is Zn minus 1x modulo rational equivalence. So let us define a map from Cartier divisor. Given a Cartier divisor, let us define a n minus 1 dimensional cycle. So if D, which is U alpha comma F alpha, okay, this is a Cartier divisor, so define for a subvariety of codimension 1, or for V in X, where V is integral, so V is a irreducible cycle, so V is integral of dimension equal to n minus 1. So for every such V, define order of D at V. So this is order of D at V. So this is given by so to define this, I'll have to first find a U alpha which intersects V. So this is equal to order of F at V, F alpha at V, where alpha is such that U alpha intersection V is non-empty. So all the U alphas cover my variety, and therefore there will be at least one open set which intersects V, and I want to define order just like we define order of a function at a codimension 1 point. So this was, if you remember, I just take the local ring of the generic point of V and go modulo this element, not go modulo, if this no, it may not be element of the ring. Write it as a ratio, and then numerator and denominator you define separately order, and then take the difference. This was all discussed in Nitin's lectures. So this definition makes sense. Okay, so the question is, I have made a choice of U alpha, an open set which intersects V. Is this order independent of this choice? It is, because if U beta also intersects, then F alpha and F beta differ by a unit, so therefore order is going to be the same. So this is well defined, and then I define so given a Cartier divisor, I define this cycle summation of summation over V, and what is the coefficient I give? Exactly like we do for functions, order of D at V. Sorry, this is maybe not be visible. So summation over V, and here I use, let me say NV, where NV is equal to order of D at V. Okay, so this is like, this gives us a little bit more flexibility. So because instead of defining divisor given by just one function, we are using different functions. Okay, so we of course get more divisors. And one thing to note is that so this gives us this map from Zn minus 1x to An minus 1x. Is this map surjective, or what do you think? Yeah, I meant a map from I meant this map actually. Sorry about that. So I meant this map. This map is already there. This is the arrow I should have pointed to. So it gives a map from Cartier divisors to Zn minus 1x. So when x is non-singular, the exercise is to check that this is actually surjective. Okay, so let me make one more definition, because after which it will be clear why this is the case. A Cartier divisor is called effective if all the F alphas, so there are two possible definitions. One is if all the F alphas can be chosen, or if let's say Cartier divisor my F alpha U alpha is effective if all the F alphas are actually in my ring. I'm not saying units, but they are actually sections of my structure sheaf. Okay, So one way to think about this is that it is given by, so if I have elements of my ring, I can take the zero locus of f alpha,
just
or
minus 0 for minus 0 for the
no, that is already there.
minus 0.
Where? Here?
Minus the set 0.
It is not required because
0 function has no Cartesian.
No, but I start with a Cartesian divisor. They are already non-zero.
Yes.
Okay, yeah. So, effective means basically they are given by non-zero functions, and if I look at the, then I can generate the ideal sheaf using f alpha. On each u alpha I generate the ideal sheaf, and they will match because on intersection f alpha is defined by f alphas differ by units. So therefore effective Cartesian divisors they are basically the same as locally principal ideal sheaves. So so obviously given a Cartesian divisor I can generate the ideal sheaf, and conversely if I am given a locally principal ideal sheaf, I can choose an open cover where it's actually principal, and on each open set I can choose a generator, that is my f alpha, and they will of course differ by unit, so I can also go back. So effective Cartesian divisors are actually defined by divisors, effective divisors which are given by one equation locally. So when my x is non-singular, every effective divisor is given by one equation, and therefore all effective divisors actually are effective Cartesian divisors. And so then there is a simple exercise to show that this is actually surjective when x is non-singular, because any element here can be written as difference of effective divisors, and effective divisors it's given by locally principal ideal sheaf. So that is a simple exercise. I can see that most of you already know this.
Non-singular in codimension.
Non-singular in codimension 1 is not enough, because I want the ideal sheaf to be actually locally factorial may be enough. Locally factorial is enough, but only codimension 1 local rings regular is not enough.
Actually, all this works for all algebraic schemes with no restriction. It is done in my slides.
Which is done in?
My slides, notes, everything. He's doing a special case which is easy to state, and I wait for it. No restrictions are needed. Nothing.
No restriction?
No, you don't even need a variety, you don't need integral, you don't need nothing.
No. For every divisor to be Cartesian.
Not every divisor, but to set up all this Cartesian divisor.
So you don't need to work over K, right? That is what you're saying.
No. I mean, your algebraic scheme doesn't have to be a variety. No.
Correct. You're right. But the statement I'm making, so for example, as what you said, every divisor or every cycle comes from a Cartesian divisor.
Special to local factor.
Only if the scheme is non-singular or locally factorial is good enough. So it does not. Normal is not enough. Not enough. Because you have to.
One example to keep in mind.
What height, what preconditions
To be principal.
that works? What do you do?
Height 1 so what is an example of a ring, normal ring, where height 1 primordial is not principal? So any non-UFD. So
There will be height 1 prime, this is not this.
there will be. If all height 1 primes are, then it's okay. Any non-UFD normal ring will be an example. I don't know of an explicit one offhand. Yeah.
Very quadrant surface.
Okay. See, the point is the ideal has to be principal not just at height 1 primes. It has to be principal at every local ring. the equation defined by that ideal has to be principal. The divisor has to be locally principal everywhere, not just in a codimension 2 open set.
Normal surface there is this will take similar points.
Yeah, at that point it will not be principal. Yeah.
Locally factorial is enough.
Yeah, locally factorial is enough.
Some multiple of the divisor might be cut here, but all
Multiple of a divisor. No. Every effective divisor is actually Cartier because it corresponds to a scheme.
okay, every effective divisor, not every divisor.
No, and then any divisor is difference of two effective divisors, and I can of course so in Cartier divisors we define Cartier divisors as a quotient of two sheaves of groups. So of course there is a group structure. I can add Cartier divisors. What is the addition or the group operation on Cartier divisors? I just multiply these f alphas. Okay, so from Cartier divisors we can go to codimension 1 cycles. Now we want to understand this link. Okay, so the point is, maybe I should first define equivalence of Cartier divisors. So this board somehow I want to keep. Okay. So of course there is or maybe I'll define here. So if f is a rational function, okay, which is just one function defined everywhere, of course that defines a Cartier divisor. So because I can just take u alpha to be x, so all these f alphas are f basically. So this defines the Cartier divisor defined by f is called principal Cartier divisor. Okay. And the group of Cartier divisors modulo principal Cartier divisors. So we will show that it is isomorphic to the Picard group. So Picard group, this is the group of line bundles. Yes, modulo isomorphism. So group of isomorphism classes of line bundles. Right. So now the theorem we want to prove is that the group of this Picard group is isomorphic to the group of Cartier divisors modulo line bundles. Divisors modulo principal Cartier divisor. Sorry? Principal Cartier divisors. Yeah, so this is isomorphism. As you can see, I am using this clumsy notation because in Fulton this is defined to be Cartier divisors modulo principal Cartier divisors. So in any case, so proof. So the question is, given a line bundle, how do I get a Cartier divisor? So if L is a line bundle, it's of course locally trivial. So I choose an open cover on which it is trivial, and I'll get transition functions. Okay, so let u alpha, or let's say let x equal to u alpha be such that, or maybe union of u alphas be such that L restricted to u alpha is trivial. And I choose trivializations, and after choosing trivializations I'll get transition functions. So let g alpha beta be the transition functions. So what are transition functions? They are, what are they? I explained this already. Okay. So what I do is let f alpha. So I pick one. I will pick one of this index. So choose alpha. Fix one index alpha naught. So fix or choose one index alpha naught and define f alpha to be equal to g alpha alpha naught. Is this defined on u alpha? Transition functions are only defined on u alpha intersection u beta, right? But to define a Cartier divisor, so I need some rational function on u alpha. So is f alpha a rational function on u alpha? Is it? Yeah, so it is a unit on u alpha intersection u beta. So of course it is an element of the function field. Okay, so f alpha is of course an element of the function field, and then you can check that f alpha u alpha, this defines a Cartier divisor. Of course we made choices of this transition function and this open cover and all that. So let me discuss one of the choice. So if I choose, let me keep the open cover same. You can go to the refinement and assume the open cover is same. So if I choose different trivializations, then what will happen? Then yeah, so then the question is, how will this Cartier divisor change? So you will have to argue that you get something, you get a Cartier divisor which differs by the original one by a principal Cartier divisor. So yeah, if you choose a different trivialization, so yes. So let me just so in the interest of time, let me just leave this. So exercise, check that this Cartier divisor. So again, if there are doubts in the discussion session, we can today's discussion session. So I will be there. So check that this is well defined. This means this Cartier divisor is well defined up to a principal Cartier divisor. Yeah, that is also possible. Yeah. Yeah. So given a Cartier divisor, given a line bundle, we got an element of Cartier divisors modulo principal Cartier divisor. So that is called, I don't know, Cartier divisor class group maybe. So temporarily it will be Picard group anyway. So now what about the other way? So given a Cartier divisor, how do I get a line bundle? So conversely, given a Cartier divisor f alpha comma u alpha, what you can do is just like we got a locally principal ideal sheaf when the Cartier divisor was effective, you just generate a submodule of the constant sheaf given by the function field. So the subsheaf of Rx, now I am thinking of Rx as a constant sheaf on X, okay, generated on u alpha by f alpha. This is actually a line bundle because locally it is defined by one equation.
One more thing.
Yeah.
OX subsheaf.
The OX, yes. The OX subsheaf. So subsheaf or OX submodule is probably a better. OX submodule is better. Of Rx generated on u alpha by f alphas, and of course on the intersection they will match because they differ by a unit. So the submodel generated, this is a line bundle because on u alpha it is generated by one element and that is an isomorphism. Remember, we are over a domain. So so this is a line bundle. Okay, and so then something I'm going to leave for you to check, and as I can see, most of you have already or many of you have already seen, but if you have not seen, this is a very nice exercise. So check that the two maps that we have defined are actually inverses of each other. So therefore this shows that the Picard group is the same as yeah, 1 by f. Okay, you're right. Yeah. So then these two maps are inverses of each other, and this shows this isomorphism. So you see, already we have a way of going from line bundles to divisors now, because given a line bundle I can actually form this Cartier divisor. Basically I'm taking local equations defining that line bundle. So I get a Cartier divisor, and Cartier divisor defines a way divisor. The problem is, given a line bundle, I only get a Cartier divisor up to a principal Cartier divisor. So I have to show that principal Cartier divisors go to 0 here. That is quite straightforward, because principal Cartier divisor is given by some equation f, one equation f, and the way divisor that is associated to it is exactly the way divisor defined by f. So that will go to 0 in an minus 1x. So therefore we also get a map, well-defined map like this. Okay, so if x is non-singular, I can just say that the image of this is the first Chern class, and then the lecture is over. Okay, so but we have to construct this first Chern class as an operator, so that is going to take time. So let me make one more observation. So given a Cartier divisor, I don't just get a line bundle, I also get a section of that line bundle. So that is something that we can observe. So for example, section of that line bundle outside the support is what I wanted to say. So first let me define what is support of a Cartier divisor. So if D, which is U alpha F alpha, is a Cartier divisor, then support of D. Okay, so this is the union of all V's where the order of F is non-zero. Okay, so this is the union of all V's where order of D at V is non-zero. So V, of course, is codimension 1. So all irreducible codimension 1 subvarieties.
I'm a bit worried about this. You are taking factorial or something.
Huh?
Are you taking locally factorial?
No.
No, then this is a bit smaller than what there are points where the order is, there are places where the order is 0 without it's being regular.
Without what being regular?
The function being regular. The rational function can have orders 0 without it's being regular.
Yeah.
And that you want to leave out of the support, and that you want to include in the support, because outside it you want the function to be regular. Yeah? So I'll give you a better definition. It's in my notes. You think of this D as a section of this sheaf,
Yeah.
X by OX, and any section of a sheaf has a support. It's a closed subset. And that is the support. That's it.
Yeah.
Otherwise, the definition goes wrong. The example of the alpha curve. You take x minus y upon x plus y on the alpha curve.
Yeah.
So, what's the support of that rational function? Now, at that point,
Correct.
order is 0, but it's not.
Correct. So I have to.
So, just say the support of D as a section of
Yes.
A star upon.
Thank you for the correction. So I think, yeah. So this alpha curve and exactly. So everything is complete actually here. So then support. So for example, now I want to say that the submodule, the OX star submodule that we generated from D has a section, right? Section has a rational section rather, right? What is that rational section? Huh? No, actual, like that submodule is a line bundle, right? So I want to say that the line bundle has a section on an open set where
But rather, this place, all that you want to say is D is a section of A star mod A star.
D is a section of?
A star mod A star.
No, I want section of that line bundle.
That's a different thing. I thought you were still bothered.
Okay. So in the support,
divisor,
correct. So it is then support of D is support of the section of D considered as a section of this sheaf. Okay, so this is a sheaf of groups. I just take the points where it is 0 and that is the support. Yeah, so this is a accurate definition. That other one was problematic for singular things like alpha.
Okay, so see what happened. I explained this point in my notes. Just look at my notes, which have been emailed to you.
Meaning, of course, a country divided up to an equivalence. So there is no, you may have something equivalent support
It's the support of the section of the quotient sheaf. So there is no equivalence. Quotient sheaf is an entity by itself. There is a section of that and take its support.
Yeah, so it is the set of, if you want to, don't go, if,
defined by many dividers.
no, not line bundle. Just the support, so D is a section of K star mod O star, then support of that. Basically all points where this F alpha is a unit. So that is the support.
It's not a not
It's not a unit, sorry.
alpha is 0.
Or may have pole or
No, support is where it is a unit.
the bad part is the support.
Okay, so where it is not a unit, the complement of that is support.
But talking because of where it is one way. But that's why we have passed no quotient. Quotient is not a sheaf in its own right. There any sheaf and a section of a sheaf. Take up all points where the stop is 0. Where the jump is 0, the stop is closed. That is the support of a section. Okay, other way.
Yes,
0. Yes, complement.
Yeah, so
because if in the stock it is 0, it's 0 and negative.
So I think there are two concepts: the sheaf being 0 at a certain point versus a section of the sheaf being 0 at a certain point.
Yes, that means 0 in the stock. Section is 0 in the stock, that means it's 0 in a whole tiny unit. And so that's always an open set where the stock is 0 in all. Complement of that.
So the point is that the line bundle that we get corresponding to this Cartier divisor on, let's say, this open set U alpha, it has a natural section given by F alpha itself, because it was generated by, the natural section given by 1 by F alpha, because it was generated by 1 by F alpha. And so therefore Cartier divisors give us line bundle together with a section defined on an open set. So that is one of the observation we want to make. So given, so D, so let's say so D is a Cartier divisor, and then the line bundle associated to this will be called as OXD. So this is the line bundle defined by this as submodule of Rx.
This is also the dual of the ideal sheaf that we get.
If D is D is effective, then only you can talk about ideal sheaf, right? So this OXD makes sense for any Cartier divisor. So this OXD has a section on, let's say for example, take one of the U alphas. On U alpha, it has the section given by 1 by F alpha. So on an open set, open set. Okay. So which is in fact I can take this section and I can
Right, F alpha G by H and take the zeros of each, like the denominator 0 out. You want the section open set.
You will need to take the section 1.
huh?
You will need to take the section 1.
Yeah. Actually, you're right. So OXD, this was defined as of Rx, okay, and as a OX submodule. Now the question is where. So now OX itself is a OX submodule here. So now if I look at the points where the section 1 is defined, yeah, section 1 is what. So if I look at the all points where 1 is actually in the submodule OXD, what are all those points? So this is maybe another way of defining support now, but I don't know whether it will exactly agree with this. So let's say set of all points P in X such that 1 belongs to OXD. This is actually I don't know, the complement of this is what we actually want as support. So this is an open set. This is an open set U, and the claim is U is actually complement of the support of D. Now with this modified definition,
Two sector.
yeah. See, 1 is a rational section of this line bundle. So 1 is a rational section of this
He's
line.
asking what do you mean by 1 belongs to.
So that is as the stock of ONC.
Yeah. So 1, yes, correct. Yeah. Look at the locus of all points where 1 belongs to that point. So that is an open set, because if 1 belongs to so that is an open set, and on this open set, this 1 is a section. Okay, so on this U, this 1 is a nowhere vanishing section, in fact. So on U, so we get a nowhere vanishing section. So Cartier divisor is giving us a line bundle together with a nowhere vanishing section outside its support. So that is the summary. So I want to make a sort of definition which to me it looks.
So if we assume locally factorial, so then you mean the map from peak x to ADX?
Yeah. AD minus. Yeah.
But we are still now, until now we are not assuming.
No, we don't want to assume locally factorial because we are going to replace x with the sub-varieties, like the proof will use, so we cannot assume x.
So far x is not in finite dimension.
Oh, yeah, it's finite dimensional.
Okay.
Everything is finite scheme over. In fact, I am only dealing with integral varieties right now. So for this discussion, because I am talking about function fields, etc. So all this discussion, the Cartier divisor definition can be made for non-integral schemes. So you invert non-zero divisors. I think that is written in the notes. It's tomorrow. Okay, but for me, integral scheme is good enough. Yeah. So this is a definition. I have to admit I found it a bit artificial. So, but it is required. I'll tell you why it is required. Okay. So pseudo divisor. Okay, so a pseudo divisor is a triple L comma Z comma S, where Z in X is a closed set, closed subset, and S is a nowhere vanishing section of L on X minus Z. So I'm given, of course, and L is a line bundle. Yes. L is a line bundle on X. Okay, so L is a line bundle on X, and I'm given a nowhere vanishing section on an open set. The complement of that I call as Z. Okay, so this is called a pseudo divisor. See, the reason why we are cooking up this thing is we want something in between. So Picard group is line bundles. Cartier divisors, modulo principal Cartier divisors is the Picard group. But before going modulo, like a Cartier divisor defines a line bundle together with a section which does not vanish at outside the support. So we want to somehow bookkeep this this Z for later. I will pinpoint where it may be needed. It is possible that somehow at least the things I am doing, maybe this is not needed, but this definition will be used by others also. So let us keep this. So this is what a pseudo divisor means. It's line bundle together with an extra data. Z is allowed to be equal to X. In that case, it is just a line bundle. Okay, so for all purposes, if you want to think of pseudo divisor, if it's too much of data, if it's hampering your understanding, you can just think of pseudo divisor as a line bundle for the purpose of this lecture. Okay, so but this is what it is: line bundle together with a nowhere vanishing section on an open set. The open set is allowed to be empty, so then I don't have any section. Okay, I don't need a section. Huh?
There is some equivalence on these two things.
Yeah, equivalence is given by isomorphisms of line bundles taking that section to the section. So that is Z is the same. Yeah, if Z is different, it's a different pseudo divisor. Yeah, so equivalence is given by isomorphisms of line bundles preserving the section. Okay, so why do we want to keep that Z? So let us. So given a pseudo divisor, so if again we'll use D is a triple, let's say D, okay, and support of D will mean Z. Okay, support of D will be Z. No, but you see, I have a nowhere vanishing section outside Z. So if it's not codimension 1, L is like almost like trivial. So there are restrictions on what. Right now there is no restriction. Yeah, but that is only there for normal varieties. So right now this is the definition. So what we want is that so given a pseudo divisor D, okay, we want to construct, so we will construct a map. Let me call it D dot, okay, so from zk minus 1 x to, sorry, zk of x to a k minus 1 of x. So in other words, what we will do is, given a pseudo divisor and a k cycle, so k is any integer from 0 to the dimension of the variety. So given a pseudo divisor and any k cycle, we will construct a k minus 1 cycle. So in some sense we are constructing the class, sorry, k minus 1 class in this chow group. So it will be only well defined as a class. Okay, so the cycle will have choices, and so that will not be well defined. So we will construct this class, and then we will show that this actually factors, this gives a well defined map from akx to ak minus 1x. So finally we want to show that this intersection with D, so I am calling this map intersection with this divisor. Intersection with this divisor gives a map from akx to ak minus 1x. So this is sort of a very small example of intersection of cycles that will come up later. So this is not very difficult to define. So what is this map? So if I just have to define it on the free basis here. So if V in X is an irreducible k-dimensional subvariety. Okay, and let's call this, give this name inclusion J. Then I want to pull back the pseudo divisor. Now how do you pull back pseudo divisors? I can quickly write down the definition. The point is, you pull back the line bundle and you pull back the closed set, it may very well happen that the closed set is the whole thing, but who cares, closed set is allowed to be the whole thing in a pseudo divisor. And outside the closed set there is a section. If the closed set, inverse image of the closed set is the whole thing, then that section you just forget about it. So yeah, so the point is, for a map I can pull back pseudo divisor. So J upper star of D, okay, so this is nothing but J upper star of the line bundle and Z intersection V, or rather J upper star of Z if you want, comma section. You only keep the section if this is not whole of V, okay, otherwise it is, there is that data is I don't know what to put in that triple, that's 0, yeah, 0, yeah, then this is 0, yeah, correct. So J upper star, so this is the pullback of the pseudo divisor, and then given a pseudo divisor we want to define a well-defined class. So of course, given a Cartier divisor we have defined, so given a line bundle we know how to construct a Cartier divisor, and given a Cartier divisor we have defined a cycle. But now what we want to do is, we want to define this class in the support of D intersection V. That is the extra detail that we want. So let me write down what. So let's say, okay, so proposition. So let D be a pseudo divisor so, or let's say L, let me give names, LZS be a pseudo divisor. Then it is represented by a Cartier divisor whose support is contained in Z. That is the claim. So then this is represented by a Cartier divisor whose support is in Z. The support of that. See, there is something called support of a pseudo divisor. The support of a Cartier divisor can be smaller than that.
You have to explain what the word represented means.
Yeah, so I have to. So what does represented mean? So the point is, given a Cartier divisor. Yeah, I did not write it clearly. So given a Cartier divisor, we got a line bundle OXD and a section outside its support, right? So so given a Cartier divisor, I get a pseudo divisor, line bundle and a nowhere vanishing section outside some closed set. Okay, so by represent I mean, so that is let's say Cartier divisor direct such that is there exists so that is OXD, that is support of D is contained in Z.
Yeah, and you are starting from the wrong side.
Yeah. That is support of D is contained in Z, and OXD is isomorphic to L, and this isomorphism takes this section 1, rational section 1, or to this S. So that is the restriction. Correct. Yeah. So this OXD comes with this section. This 1 is confusing. So this there is a let us use this notation SD. Okay. So this section will be called as SD. Nowhere vanishing section denoted by SD. Okay, so such that SD goes to S. Now, of course, this is not defined on the whole thing, so you have to look at on SD restricted to X minus Z goes to S. S is anyway defined on X minus Z only. So this is what we want to show. So in other words, what we are saying is, given a line bundle, I get a Cartier divisor, but if I already have a nowhere vanishing section of that line bundle on an open set, I can manage to get a Cartier divisor outside, in the locus where that section vanishes. So I can, that is the idea. Yes, so how do we get this? So we will go back to the construction of Cartier divisor using line bundles. So we had this, so let G alpha beta be the transition functions defining L. What I mean is I choose an open cover which trivializes L, and then I look at the transition functions G alpha beta. U alpha is the open cover. Okay, so this is and then how did we get a Cartier divisor? We said define F alpha to be equal to G alpha alpha naught, where and choose an index alpha naught. And then this F alpha comma U alpha defined a Cartier divisor. Now I want to modify this Cartier divisor using this section. So shall I actually write down all this U alpha? And I'm slightly confused. Okay, so now what is this section? What does this section mean in terms of this transition functions? And so the point is this section section corresponds to.
You just take this section. Generically, it's a rational function.
Yeah.
Take its divisor. Divisor. It makes sense to take divisor of a section of a line bundle. No? First of all, you say every rational section of a line bundle has a divisor.
Yeah. Yeah. Actually, that's a cleaner way. That produces D. And that is locally given by. Actually, this is much cleaner way of doing it. Yeah. So let me.
That is the principal divisor corresponding to the Cartier.
I will not call it principal divisor. That we reserve for actually sections of OX. Okay, but yeah, so that is a better way. So instead of this G alpha beta and all that. So what we do is, given this section, we just define the divisor of S. Yes. So divisor. Wait a minute.
Because it's locally trivial, we are order of addition of this. And so that gives you the divisor.
It will give effective divisor.
Huh? This is a regular section, therefore it will be.
So every pseudo Cartier divisor is giving a effective Cartier divisor. Something.
You have not said effective.
I have not said effective.
So what take the divisor of S.
Okay. No, divisor of S, will it not be a regular effective?
See, S is locally a minority.
Oh yes, S is only defined on an open set. It's a rational section. Sorry about that. Yes. So divisor of S. So this is the Cartier divisor, which we need. So what is this divisor of S? I just need to define order of S at local rings of codimension 1 points or codimension 1 subvarieties, and for that I can choose a trivialization, and then S will actually become a function, regular function. Any two different choices will give me a function which differs by. It will be a rational function. And any two different choices of trivialization will give me something which differs by a unit. So the order is well defined. Okay, so therefore this divisor is well defined, and this is my Cartier divisor. Okay, so this is good. Now what we want to do is define this map from zk of x to ak minus 1 of x. So how do we do this? So I take let's say I take V, which is a k-dimensional subvariety, okay, and a class of V. I am going to send it to the class of J upper star of D, where J, so let's say V, the inclusion map from V to X is J, and send a class of V to the class of J upper star of D. I can pull back pseudo divisors. Basically, I am pulling back the line bundle, and then every line bundle gives me a divisor. I am taking that divisor. It's as simple as that. But why this language of pseudo divisors? Because if D that is for bookkeeping, in the sense if D already is a well-defined divisor rather than just a line bundle, then you see it's then it has a support, it's given by a Cartier divisor, it's a well-defined support, and then I can choose this J upper star D.
Your notation on the right hand side, D means a pseudo divisor.
Yeah, D means a pseudo divisor. Yeah, D is a pseudo divisor.
Your notation.
Sorry, this I all have to erase this.
Said it here, but there.
Correct. This board is in between where D is something else. Now here again D is a pseudo divisor. So yeah, so I pull back pseudo divisor, and then this pseudo divisor is represented by a Cartier divisor, and then of course Cartier divisor represents a cycle. So that cycle I take. Okay, so there is no question of well defined. I am just defining it on the basis. So therefore this gives a map. But okay, no. So there is a problem.
Repeat your comment.
So
Yes, sir.
You can pull back pseudo divisors, so this is possible, but you cannot pull back Cartier divisors. That's why you went to pseudo divisors.
Correct.
What you
Yeah.
to tell you stop.
Correct. So So why pseudo divisors? Okay. So the point is Cartier divisors pulling back is not. So that is not clear. How do you pull back Cartier divisors? But if you take Cartier divisors modulo principal Cartier divisors, that is line bundles we can always pull back. Okay, so that is the point. So but if suppose there was a situation where I can pull back the Cartier divisor, which means that this Z then I want to bookkeep that also. That is the reason for this definition of pseudo divisors. So but simplistically, like if you want to focus on the main idea, what we are doing is I want to pull back a Cartier divisor, I convert it to a line bundle, and I pull back the line bundle, and then I form a divisor. It's well defined up to rational equivalence. That is what I am doing. So why this pseudo divisor? Because I want to make the comment that this J upper star D is actually defined in AK minus 1 of not X but the support of D intersection V. Okay, so for this this thing which may be needed later on. So this is a cycle not just defined in AK minus 1 of X, but up to rational equivalence. It's well defined in this smaller subvariety. That is the reason.
One more point of notation.
Yeah.
Since it's a pseudo divisor here, by support you mean Z.
Correct.
Because
By support.
on this board it says D content.
No, support of D is Z. Yeah. So.
Well defined is if we change this choice of Cartier divisor, I think we need to check for well defined as well.
If you change the Cartier divisor.
Yeah, I mean this D which represents the pseudo divisor.
Oh, yeah, correct. So the point is, if Z is not equal to X, okay, then you see this D is actually uniquely determined, because then any two rational functions, they will have to give the same S on an open set. So therefore it is actually uniquely determined. So yeah. No, because yeah, it does not matter actually. Yeah, I'm only taking pseudo divisor. It does not matter. So what? Yeah, but anyway, I can give this as an exercise here. Exercise, because we are not going to need it here. So if Z is not equal to X, then D is uniquely determined. Sorry, my D is a Cartier divisor here and a pseudo divisor on these three boards. So determined. Okay, so in any case we have defined, so this is not the main work. Okay, so the main work, so it's very easy to take a actual, so this is anyway a free abelian group. I can send the basis wherever I want. There is no checking required. So the checking is, the main work is in showing that the rationally equivalent cycles here go to 0 here. So that is the main work. Okay, so I have this, so therefore this is for V, and so therefore for any alpha in any alpha in zk of x, we have this element d dot alpha in ak minus 1 of x, but actually it is also defined as in ak minus 1 of, so it is actually also well defined as a element of ak minus 1 of support of d intersection support of alpha. Okay, this we may need for later use. Okay, but right now, just to focus on ideas, you just think of d dot alpha as an element of ak minus 1x.
But why that inclusion?
Sorry, not, that is a typo. So let us write down some properties of this d dot alpha. Okay, so there are some. So now I'm taking a pseudo divisor d and a cycle, not a class, cycle alpha. So the following are satisfied by this this map d dot. So okay, so let me list some obvious properties. One obvious thing is that this is a group homomorphism because I defined it on a basis. Okay, so but because Fulton states it, I'll also state it. So d dot alpha plus alpha prime is d dot alpha plus d dot alpha prime. Okay. Second, if I actually if d is the sum of two pseudo divisors. Now what do I mean by sum of two pseudo divisors? So as I said, you can think of pseudo divisors as line bundles first. Okay, so what is sum of line bundles? Actually, it means tensor product of line bundles. Now, if I take tensor product of line bundles and I have a rational section of each of them, I get a rational section of the tensor product. Okay, I'll have to choose a suitable open set on which both are defined. So basically, I have my z will be the union of both the z's. Okay, so the sum of pseudo divisors is defined as tensor product of line bundles, and you do the obvious thing for sections and that support. So d plus d prime dot alpha is equal to d dot alpha plus d prime dot alpha. This is also clear because if I pull back two line bundles, then taking their divisors, now of course I have to take divisors with this constraint that they are supported in that z, so that also is compatible. So this I am also going to sort of hand wave because hand wave, I'm saying the word hand wave not because it's difficult, but it will need writing down, but I don't want to write down here on the board. Okay, so this actually directly follows from definition. The third one is really important for us. I mean, of course the first two are also important, but the third one will need, so that I will have to write down the proof, is called projection formula. Okay, so this says that if x prime to x, let's say f, is a proper morphism, if f from x prime to x is a proper morphism, and let's say alpha is a k cycle on x prime and d is a pseudo divisor on x. D is a pseudo divisor below, so you can think of it as this proper morphism as vertically coming down. So D is a pseudo divisor below and alpha is a cycle above. Then what I can do is I can pull back this pseudo divisor, then take dot product with alpha. Now this is a well-defined class of ak minus 1 x prime. In the morning we have seen how to push forward using proper morphisms. So now I can push this forward. And the claim is that this is equal to, instead of doing all this, you just push forward alpha and then take dot with d. So that is, so d dot push forward of alpha. Okay. Surjective is not needed. It's not needed.
No, that was only part of the proof.
Yeah. Okay, so this projection formula, so let us prove this. I mean, prove means it's essentially we are going to refer to the result. The main work was done in the morning, so that, but let us observe that this is true. Okay, so proof of C. So there are some immediate reductions we can make. So first, I can assume that alpha is just given by one subvariety V, closed subset V. Okay, right? And so I can replace x prime by that V. Then V to x is also proper, right? So because closed immersion followed by proper is proper. So I can replace x. So let's say alpha is equal to V. So without loss of generality, and then without loss of generality, I can assume alpha is actually V. And since I'm pushing forward this class, what happens outside V, I don't care, because I'm not worrying about rational equivalence above. Okay, so therefore I can assume x prime is equal to V. And below I am anyway, the cycle is going to be well defined as a class in support of alpha. So I can even assume that x is actually image of f of V. This is the reduction we can immediately make. Okay, so now now there is one more reduction we can make. So we want to show that yeah, so then what is the push forward of V? So in this case, what is the push forward of V as a cycle? Huh? As a cycle. In the morning, what is the definition of push forward map? Class of FV, no. Time the degree of field extension. Of course, if f of V and this is of the same dimension, right? If this is not of the same dimension, then you see, this both sides we have to argue are 0. Okay, so I'm going to leave that case and do the non-trivial case. So so let's say n is the degree of extension of RV prime, RV over X, or yeah, so V is equal to X prime. Okay, now we have to Rx. Yes, Rx. Oh, I'm lagging behind. So RV, let this be the degree of extension. What is the right hand side? It is d dot this f star alpha, right? So
You already written what is the pro star alpha.
yeah, so no, somehow I want to reduce it. I want to say locally I can reduce it to the case where D is actually a principal Cartier divisor, because I can work Zariski locally. So that I just want to everything else.
Divisor you can write as principal divisor somewhere.
No, you can't do that. So not everything is sum of principal divisor. Then all line bundles will be trivial.
Locally is saying that.
Yeah. Okay, so this I am a little bit blanked out. So D dot F star alpha. So we want to show this equality. Okay, let me do case 1. Let me package whatever I know as case 1. So case 1, D is actually a principal divisor. Okay, so D is actually given by one equation. In that case, what happens? So in that case, oh, that is a real problem. G or maybe R. I think R is the letter used in the book. So so let's say D is actually a principal Cartier divisor. Okay, so in that case what happens? So in that case, what is the pullback of D? It will be the principal Cartier divisor given by the pullback of R. So small r considered as a function here, right? And when I take this dot product, what is this? I just take the divisor associated with R, right? So therefore, if I look at pullback of this R, and then I take the divisor given by this, right? And then the push forward of this. The push forward of divisor given by a rational function is the divisor given by the norm of that function, right? So this is equal to the divisor given by the norm, but R is in the base, in the field below. So what is the norm? The norm is R to the power degree of that extension, n is the degree. So this is the class given by R to the power n, which is equal to n times the divisor given by R, right? Yeah. So what I am missing, the reason I blanked out is, although this d dot alpha is an element defined in this ak minus 1x, okay, so I have to write this carefully where everything makes sense as cycles, then I can work Zariski locally, and I can actually do this. So let me do this part cleanly in the next lecture. So, and I'll state what is the main thing that we have to do next. Okay, so where will this projection formula be actually used? So now what we want is, if let's say I have two Cartier divisors, so suppose pseudo divisors, d and d prime are pseudo divisors. Then every pseudo divisor actually defines a cycle, right? So I can take the cycle of d prime, which is in a n minus 1 of x, where n is the dimension of x, right? And I can do d dot of this. Is it clear what I'm doing? Yeah, so every pseudo divisor gives a cycle, because every pseudo divisor is represented by a Cartier divisor. Cartier divisor, by taking that order, gives a cycle, right? So this is that cycle. And now when I take square bracket, I am taking that cycle. What is d dot of a cycle? So this is this d dot alpha that we have constructed here for any k cycle. So now in this case, this is a n minus 1 cycle where n is the dimension of the variety. So d dot of this will be a n minus 2 what? Class in a n minus 2x. It is not well defined as a cycle in general. Okay. So this belongs to a n minus 2 of x, okay. But I can also take this. Now d prime is also a pseudo divisor, so I can interchange the role. I can take d prime dot d, okay. So the main, so this is also a class here. So the main theorem that we want to prove is that d dot d prime, this is equal to d prime dot d in as a class in, of course here, but as I said, the reason for this pseudo divisor is bookkeeping of the support a little bit better. So in actually a n minus 2 of support of d intersection support of d prime. Okay, so this is the main theorem we have to prove. This is going to take a little bit of commutative algebra and blowing up, this technique from blowing up, where we are going to use this projection formula. Okay, so that we will do in the next lecture. But we will also see, we'll also discuss blow-ups in this discussion session if there is time. So if you have other doubts, of course, that gets priority. Okay, so I think I'll stop here.
This passes through the linear equation is in ZK, rational equation is in ZK, right? Before it. Otherwise, this class of d prime is a class only. It is not a cycle.
He is saying that your square bracket d is defined as a class.
Correct.
No, you said cycle right?
No, but we need to should be defined like that. Dot product is a class.
Yeah, it's a class.
It is well defined because we defined it as a map of free abelian groups. So Okay. Yeah, okay. This is a cycle. Square bracket D, I want to denote it as cycle. Is that a bad notation? Maybe I can choose another one.
Sir, how is to like getting a cycle for
Zero divisor club gives you Cartier divisor.
but not even
You have not defined it for pseudo divisor yet.
What?
You have not defined
I have
the
defined.
cycle for a pseudo divisor.
No. Pseudo divisor gives Cartier divisor. And for Cartier divisor.
Several Cartier divisors is what you mean.
Yeah, so so correct. So that statement that uniqueness that I wrote, that if Z is not equal to X, then I get a unique Cartier divisor. That I think I wrote as an exercise. I think I will do that as an that exercise.
The Z is equal to X.
No, in this case Z is not equal to X because this is a.
No, imagine Z is equal to X. Then there are several Cartier divisors which give the same line number, right?
Yeah.
But they have different wave divisors,
Correct.
which are only rational equivalent.
Yeah.
Therefore, that construct bracket is to be interpreted as a class.
Okay. So I think this is a good question. Okay. So what we are going to do. So let me tell you how we will resolve this. So first we will assume that D and D prime have proper support. Like Z is not the whole of X. Okay. Using that, for that we will prove this situation. Okay. So and then once we do that, then we will show well-definedness. So maybe this needs more explanation. So this I will explain later. But yes, so this is a good question. So first we will do it for pseudo divisors with proper support. Actually, I can just do it for Cartier divisors. Huh?
You don't have to do so many cases. Do it for Cartier divisors.
Yeah, Cartier divisors. So there is no need for doing it for pseudo divisors. So let's say for two Cartier divisors, we will do this. So then it is. Yeah, correct. For pseudo divisors, it will be a consequence that it will be well defined later. So this is this should have been Cartier divisors. So that was a mistake. So this is the main.
Don't call it cycle.
Which?
Okay.
Now it is cycle.
Now it's a cycle.
Because I don't want to call it class. I have not shown well definedness of that dot product. So therefore, this is a cycle, and this dot product is a class. Okay, so this equality is what we have to show in the next lecture.